Imagine that a decision you made today, seemingly insignificant, could alter the course of world history. Sounds impossible? Science has proven that this is not only possible, but happens constantly all around us. This is the power of the butterfly effect, a discovery that shook the foundations of modern science. In 1963, Edward Lorenz, a meteorologist at MIT, made an error that would forever change our understanding of reality. Working with climate simulations, he entered slightly rounded data into his equations, a microscopic difference. The result was surprising. Distinct predictions emerged after just a few simulated days. It wasn't a computer glitch. And you know what's most interesting? Lorenz discovered that this doesn't just happen with weather. It's happening around us all the time, in places you can't even imagine. Lorenz christened his discovery with a question that became legendary. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The answer is, theoretically, yes. The atmosphere contains billions of trillions of molecules constantly interacting. A network so dense that a microscopic disturbance can amplify through layers of interaction until it alters global weather patterns. But here's what makes this revolutionary. Chaotic systems aren't random. They follow rigorous mathematical laws, but are extremely sensitive to the starting point. It's like balancing a pencil on its tip. Mathematically possible, practically impossible to predict how long it will stay upright. This sensitivity to initial conditions appears in surprising places. In traffic, a single driver braking unexpectedly can create traffic jams stretching for miles. Animal populations can thrive or go extinct based on seemingly trivial fluctuations. Even your heart exhibits healthy chaotic variability. When this variability disappears, it can signal serious problems. To better understand this phenomenon, scientists study what they call the logistic map, a simple equation that models population growth. With low growth rates, the population stabilizes predictably. But when we gradually increase this rate, something remarkable happens. The population begins to oscillate between two values, then 4, then 8, in a cascade that accelerates exponentially until complete unpredictability. In this turbulent regime, a microscopic difference in initial conditions produces distinct results after just a few cycles. Within this chaos, however, there are mysterious windows where order temporarily returns. Islands of predictability in the ocean of uncertainty. This discovery has impressive parallels in the real world. Imagine a pendulum being pushed rhythmically, or particles in high-energy accelerators. With weak disturbances, trajectories are smooth and predictable. But intensify these disturbances, and something extraordinary emerges. Regions of perfect stability surrounded by total turbulence. It's like finding calm in the middle of a storm. Particles in these regions maintain regular patterns, while around them they follow unpredictable paths. This geometry explains phenomena ranging from the stability of multiple solar structures to the erratic dynamics of asteroids in the belt between Mars and Jupiter. Some asteroids follow stable orbits for millions of years, while others, apparently similar, are ejected from the solar system in a matter of thousands of years. The difference? Their initial location relative to these mysterious regions of stability. This coexistence between order and turbulence isn't just mathematical curiosity. It explains everything from the stability of planetary orbits to the functioning of nuclear fusion reactors. Unpredictability doesn't eliminate order. It creates a richer reality where both coexist. The visual beauty of turbulence manifests in fractals, structures that reveal infinite detail at any scale. Imagine shapes that, when magnified, show similar patterns at smaller scales, like mathematical Russian dolls. The Mandelbrot set, generated by a simple equation, produces infinite complexity from an elementary rule. Magnify any part of its boundary, and you'll discover details that echo the original shape, but never repeat exactly. This self-similarity appears throughout nature, in the branching of lungs, vascular networks, lightning structure, and even in the distribution of galaxies. Fractals aren't just mathematical art. They measure surface roughness, analyze economic signals, and evaluate the efficiency of biological networks through dimensions that aren't whole numbers, capturing aspects of complexity impossible to describe with traditional geometry. Chaos permeates from the molecular level to the cosmic. Chemical reactions like the Belousov-Zhabotinsky create hypnotizing patterns that reveal how sophisticated life can emerge from simple processes. Imagine a chemical solution that pulses between different colors, blue, red, yellow, creating waves that propagate across the surface like a chemical heart beating. This reaction was fundamental to understanding how living systems can arise from inanimate matter. Animal populations also dance to the rhythm of chaos. The classic predator-prey model, when we include realistic factors like resource competition and limited environmental capacity, exhibits surprising chaotic behavior. A lynx population in Canada can grow exponentially for a few years, then enter dramatic collapse. This cycle never repeats exactly the same way. Small variations, a slightly colder season, a minor disease in the rabbit population, can determine whether a species thrives or disappears from an entire region. What's interesting is that ecologists have discovered similar patterns in forests, oceans, and even in human populations throughout history. Entire civilizations may have flourished or declined due to fluctuations that, viewed in isolation, seemed insignificant. In modern meteorology, even the most powerful supercomputers can only achieve reliable predictions for about a week. This isn't a technological limit, but a fundamental barrier of the chaotic nature of the atmosphere. Think about it. We have satellites that measure temperature, humidity, pressure, and wind speed at millions of points around the globe. We have algorithms that process trillions of calculations per second. Even so, predicting whether it will rain in your city 2 weeks from now is impossible. This happens because the atmosphere is a system with countless trillions of molecules interacting simultaneously. Each molecule follows the laws of physics, but collectively they create behavior that defies any attempt at control or long-term prediction. It's like trying to predict the outcome of a billiard game where each shot affects the position of trillions of balls simultaneously. Engineers, however, have learned to use chaos creatively. Chaotic lasers, which produce light with unpredictable patterns, are used in ultra-secure communications. Since the signal is chaotic by nature, intercepting or deciphering it becomes an almost impossible task. Cryptographic systems based on chaos offer security that derives from the fundamental laws of mathematics, not just current computational difficulty. Here something fascinating emerges: the concept of emergence. Emergent properties are characteristics that cannot be predicted by analyzing components in isolation. Consciousness emerges from individual neurons, although no single neuron is conscious. Financial markets exhibit behaviors that transcend individual decisions of participants. This emergence happens at the edge of chaos, a critical region between total order and total chaos. Systems in this zone are intricate enough to generate novelty, but stable enough to preserve useful structures. Life, societies, and even artificial intelligence operate on this impressive frontier. Artificial neural networks demonstrate this clearly. Each neuron performs simple operations, but collectively, they can recognize patterns, learn abstract concepts, and create original art. Intelligence emerges from organized complexity. It's remarkable to realize that modern artificial intelligence systems, like those that generate images or answer elaborate questions, operate exactly on this frontier. They're chaotic enough to be creative, but ordered enough to be useful. This principle extends even to the functioning of our brain. Individual neurons are simple. They receive signals, make a basic calculation, and decide whether to fire or not. But when 86 billion of these neurons connect through trillions of synapses, something emerges that we call consciousness, memory, creativity. Every thought you're having right now is the result of this chaotic dance between billions of brain cells. The same principles that make weather unpredictable create beauty in fractals, in hurricane spirals, and rhythm in river turbulence. A hurricane spiral follows the same mathematics that governs the growth of a nautilus shell or the distribution of seeds in a sunflower. This universality suggests that beauty isn't an accident, but a natural consequence of the laws governing sophisticated systems. Musicians have discovered that compositions with controlled chaotic elements sound more interesting than ordered or random melodies. Music reaches its peak at the frontier between predictability and surprise, exactly where chaos theory operates. The butterfly effect transforms our understanding of responsibility and consequence. If microscopic actions can have colossal impacts, then every decision, however small it may seem, carries genuine transformative potential. Not in a mystical sense, but a scientific one. This perspective doesn't paralyze us with the weight of responsibility, but frees us through understanding. Recognizing the impossibility of controlling all outcomes allows us to focus on what matters: the quality of intentions and the wisdom of initial choices. Chaos also teaches scientific humility. Simple systems can generate complexity that challenges our capacity for prediction. This isn't a failure of science, but a discovery about the fundamental nature of reality. There are intrinsic limits to knowledge, and recognizing them is part of wisdom. The journey through chaos theory reveals a paradoxical truth. Unpredictability contains its own forms of order. Systems that escape control still follow deep patterns, obey invisible attractors, and create structures of unexpected beauty. Perhaps the most valuable lesson is learning to navigate uncertainty without losing sight of it. In our lives, careers, and relationships, we constantly operate at the edge of chaos. Small decisions amplify through intricate networks, creating unpredictable futures. But within this unpredictability, there's space for creation, innovation, and the emergence of new patterns. Like natural systems that thrive in the balance between order and disorder, we can find strength in flexibility, beauty in complexity, and purpose in dancing with the unpredictable. The universe doesn't need to be ordered to be deeply meaningful. Sometimes the secret lies in learning to dance with the unpredictable and letting the mathematics of the cosmos show us paths we never would have imagined alone. From a simple discovery by Lorenz about rounding in meteorological data, we discovered that we live in a universe much richer, more elaborate, and more beautiful than we imagined, where every choice, every moment, every breath can be the flutter of wings that changes everything. And this makes me think, if small actions can have enormous effects, then that conversation you had yesterday, that message you sent, even this video you're watching right now, any of these things could be changing something in the world in a way we'll never know. If you were impressed by how small actions can transform entire realities, leave a like and subscribe to the channel to discover more mysteries that science has to reveal. Share this video with someone who needs to understand that we're not passive observers of reality, but active participants in the constant creation of the future. In the end, maybe this is the greatest lesson of the butterfly effect. Each of us carries a remarkable responsibility and privilege in building tomorrow, because knowledge is just the beginning.